Hey everyone, in this video we'll be looking at solving systems of linear equations using substitution. So our first example, they asked us to solve the system y equals 2x plus 5 and 3x minus y equals negative 6 by substitution. Okay, so we are looking for an algebraic solution to this system as opposed to graphing, and we have to use the method of substitution. So in order to do that, we need to isolate one of the variables in one of our two equations. So our first equation, y is already isolated, so that's been done for us. Then what we're going to do is we're going to take the expression that's equivalent to y, which is 2x plus 5, and we're going to substitute it in for y in the other equation. So what that's going to look like is 3x minus the expression 2x plus 5 substituted in for y equals negative 6. Now, just like when we're plugging in values to an equation, we want to put that value in a set of parentheses when we're substituting it in for a variable, just so that we don't make any careless mistakes. We want to do the same thing here with our expressions. Okay, keep a set of parentheses around the expression when we're substituting it into the other equation. Now, what does this accomplish? Well, what we've been able to do is take two equations in our system of linear equations and condense it into a single linear equation that we can now solve. So we can solve this by first distributing the negative. So we'd have 3x minus 2x minus 5 equals negative 6. Simplifying the left-hand side, x minus 5 equals negative 6. We can add 5 to both sides. X equals negative 1. Now it's tempting to stop here. Right? We did a lot of work already. But we have to remember that the solution of a system of linear equations is a point. So we have to find both coordinates of the point. Right now we only have the x coordinate. So in order to solve for the y coordinate, we're going to take negative 1 for x and substitute it into either of the two equations they gave us. I think it's simpler to use the first equation because y is isolated. So we'd have y equals 2 times negative 1 plus 5, y equals negative 2 plus 5, y equals 3. So the solution to this system of equations is the point negative 1, 3. And we can check that that's correct by plugging it into the equation we didn't use, which we would get negative 3 minus 3, which is in fact negative 6. Okay, so that's the method of substitution. To define our steps, first step is to solve one of the linear equations to isolate one of its variables. So in that first example, that was already done for us. The first equation was already written as y equals. If it's not, we have to make a choice as to what variable we want to isolate. Second step is to substitute the expression from step 1 into the other equation and solve for the other variable. So in that first example, we substituted in for y in the second equation, and then we solved for x. Be sure to include parentheses around the expression from step 1 when substituting. And we talked about why that's a good idea. Then we're going to take the value we got in step 2. So in the first example, that was x equals negative 1. And we're going to substitute it into either of the original equations to find the other variable. So we substituted x equals negative 1 into the first equation, and we solve for y. Once we have both the x and the y value, we write the solution as an ordered pair. All right, our next example, system is 4x equals 8y and 6x minus 4y equals 6. So since we have a choice, it's going to be easier to isolate the variable in the first equation. The variable that I think is easier to isolate is x. It's just going to give us a nicer expression than if we isolate y. But they're both pretty easy to find. So I'm going to start by dividing both sides of this equation by 4. And that will give us x equals 2y. So we've isolated x in terms of y. So we have 2y, and we're going to substitute it in for x. So our equation is going to be 6, and then times 2y minus 4y equals 6. So on the left side, we can simplify. 12y minus 4y equals 6. 8y equals 6. Divide both sides by 8. y equals, in simplest terms, 3 over 4. So we have the y coordinate. Now we need to find the x coordinate. So we'll take this and substitute it in for y in one of the two equations. Again, I think the easier choice is the first equation. So we'd have 4x equals 8 times 3/4. So this is really 8 over 1. So simplifying 8 and 4, that would give us a 2. So we have 4x equals 6. Divide by both sides by 4. X equals, in simplest terms, 3 over 2. So, writing it as an ordered pair, we have the point 3 over 2, 3 over 4. Now, just something to pay attention to is we want to make sure we're writing in the correct order, right? Because we solve for two variables, we want to write it x first and then y. Just a simple thing to watch out for. Next example, 3x minus 1/2 y equals 10, 5y minus 2x equals negative 16. So this is a good example to look at because none of the variables jump out as being easy to isolate, right? There's not a single variable that doesn't have a coefficient. So really the choice is ours. And we want to try to choose so that we have the simplest expression possible to substitute. So for that reason, I think it makes the most sense to isolate the y variable in the first equation. Because it has a coefficient of 1/2, we'll wind up multiplying both sides by 2 and avoiding creating more fractions. Whereas if you isolate any of the other variables, we would create fractional terms. Now that shouldn't be a scary thought. Fractions really aren't too difficult to work with, but if we can avoid it, it might be a smart decision. So first thing, we can subtract 3x on both sides. We'd have negative 1/2 y equals negative 3x plus 10. We can multiply both sides by negative 2. Now remember, we have to multiply both of these terms on the right by negative 2 to distribute that in. So we'd have y equals 6x minus 20. Okay, so now we're going to take the expression 6x minus 20 and substitute it into y in the second equation. So we have 5 and then times the expression 6x minus 20 minus 2x equals negative 16. So start by distributing the 5. Let's fix that. 3. So we have 30x minus 100 minus 2x equals negative 16. Combining the like terms, we get 28x minus 100 equals negative 16. Add 100 to both sides. 28x equals 84. Divide both sides by 28. And x is equal to 3. Now that we found the x coordinate, we have to solve for the y coordinate. So in this case, I'm going to substitute into the second equation here. So 5y minus 2 times 3 equals negative 16. 5y minus 6 equals negative 16. Add 6 to both sides. 5y equals negative 10. Divide both sides by 5. Y equals negative 2. So we have our x and our y value, writing it as an ordered pair, 3, negative 2. And again, if we want to check that this is correct, we could substitute 3, negative 2 into that first equation. We'd get 9 plus 1, which is in fact 10. So we know we have the correct answer. All right, moving along. Next system, y equals 4x minus 7 and 3y minus 12x equals 15. Now they've done one of the big tasks for us. They've already isolated one of the variables, right? That first equation is in slope-intercept form or mx plus b form. Y is already isolated. So we're going to then substitute this expression in for y in the second equation. So we have 3 times 4x minus 7 minus 12x equals 15. So start by distributing. 12x minus 21 minus 12x equals 15. Combining like terms on the left-hand side, we have negative 21 equals 15. So what we notice is the terms with x in them simplify. They cancel out. And what we're left with is a statement that is not true. So what does that mean about the solution of this system of linear equations? That means there is no solution. So we have no solution here. Graphically, what this would be equivalent to, if we graph both of these lines, is the lines would be parallel with different y-intercepts. Okay, so algebraically, this is what that case is going to look like. If we substitute in the expression into the second equation, we wind up with a statement that is not true. Okay, if we wind up with a statement that is true, then that would be the case where both lines are the same, and we write up our solution as all points on the line and pick one of the two lines that they've given us. Okay, so this is how it looks algebraically when we have a case with no solution. Our last example, system is y minus 6 equals negative 1/5 times the quantity x plus 1, and x plus 2y equals 14. So this is the first example that we've been given a line in point slope form. Remember, we're trying to use substitution, so we need to pick one of the two equations to isolate a variable in. I think the simplest equation to use is the second one and isolate the x variable, because all we have to do then is subtract 2y from both sides, and we'd have x equals negative 2y plus 14. So we could take that expression and substitute it in for x in the first equation. So we have y minus 6 equals negative 1/5 and then for x, substitute the expression negative 2y plus 14, and then plus 1. So simplifying what's inside of the set of parentheses, we have negative 2y plus 15. Now we have two choices here. We could either distribute the negative 1/5, or we can multiply both sides by negative 5. Since we haven't worked with too many fractions in these examples, let's distribute the negative 1/5. So we'd have y minus 6 equals positive 2/5 y minus 3. So we can subtract 2/5 y from both sides. Now in order to combine these terms, we need a common denominator. So I'll rewrite y as 5y over 5. So that means on the left-hand side, we have 3 over 5y minus 6 equals negative 3. Add 6 to both sides. We have 3 over 5y equals 3. And then we can multiply both sides by 5/3. So the 3's simplify. We have y equals 5. All right, we still have to solve for x. So substitute in, I think the second equation is the easier one to substitute into here. So we'd have x plus 2 times 5 equals 14. X plus 10 equals 14. That doesn't look like a 4. 14. And we can subtract 10 on both sides. X equals 4. So writing it as a point, our solution is 4, 5. All right, so that's how we solve a system of linear equations using substitution. Now we'll be able to extend the idea of substitution into systems that we're going to see later in this course. Okay, so make sure we understand what we're doing and just watch out for some of the simple mistakes that we can make in doing this process, because we have to do a few steps to get our solution.